The bearing capacity of soil, factors and calculations. Welcome to Blueprint to Reality, your trusted source for all things civil and structural engineering. In today's episode, we're going to discuss the bearing capacity of soil, factors and calculations. Let's dive into what bearing capacity is, the factors that influence it, and how engineers calculate it for construction projects. What is bearing capacity of soil? The bearing capacity of soil refers to the maximum load per unit area that the soil can support without failing or experiencing excessive settlement. In simpler terms, it is the ability of the soil to support the weight of a building or a structure. If the soil cannot support the applied load, the foundation may fail, leading to structural issues such as cracking, tilting, or even collapse. Why is bearing capacity important in construction? Bearing capacity is a critical consideration in foundation design. Engineers need to ensure that the soil beneath the structure can support the weight without excessive settlement or failure. Here's why it matters. Safe foundation design. Accurate bearing capacity calculations help design foundations that prevent structural failures. Prevent settlement. Knowing the soil's bearing capacity ensures that it won't settle excessively, which could damage the building or infrastructure. Cost-effective construction. Proper bearing capacity analysis allows engineers to select the appropriate foundation type and size, preventing unnecessary material costs. Factors affecting bearing capacity of soil. Several factors influence the bearing capacity of soil. These factors are important for engineers to consider when calculating how much load a soil type can bear. 1. Soil type and composition. Different soils have different load-bearing capacities. Clayey soils. Cohesive soils like clay have a moderate bearing capacity, but their strength can decrease with increasing moisture content. Sandy soils. Granular soils like sand have higher friction, which increases their bearing capacity. Gravel and rock. These soils generally have high bearing capacities due to their coarse particles, which interlock and provide strong resistance. 2. Soil compaction. The more compact the soil, the higher its bearing capacity. Loose soils have more voids, which make them weaker, while dense, compacted soils have fewer voids and are stronger under load. 3. Moisture content. Moisture content can significantly affect the bearing capacity of soil. Wet soils, especially fine-grained soils like clay, can lose their strength and become more compressible under load. On the other hand, dry soils like sand usually have higher bearing capacities. 4. Depth of foundation. The deeper the foundation is placed, the greater the bearing capacity, as the load is distributed over a larger area and deeper, more stable soil layers are reached. Foundations that are too shallow may not have sufficient bearing capacity and can fail. 5. Overburden pressure. The weight of the soil above the foundation, also known as overburden pressure, can increase the bearing capacity of the soil. This is because the additional weight of the upper soil layers compresses the lower layers, increasing their strength. 6. Soil strength. The internal friction and cohesion of the soil particles affect its shear strength, which is directly related to its bearing capacity. Soils with higher friction and cohesive properties tend to have higher bearing capacities. Methods for calculating bearing capacity. Engineers use different methods to calculate the bearing capacity of soil, depending on the soil type, depth of foundation, and other factors. Here are the primary methods. 1. Terzaghi and Peck's method. This method, developed by Carl Terzaghi and Ralph Peck, is widely used in foundation design. It involves calculating the ultimate bearing capacity using factors such as soil cohesion, internal friction, depth of foundation, and foundation width. 2. Meyerhoff's method. Meyerhoff's approach improves upon Terzaghi's method by incorporating factors for both shallow and deep foundations, as well as considering the effects of eccentric and inclined loads. This method is particularly useful when the foundation is subject to different types of stresses. 3. Punching shear method. This method is often used for foundations that are subjected to concentrated loads, such as piles or columns. The soil around these foundations can fail in a punching shear mode if the load exceeds the soil's capacity to resist it. Field tests for bearing capacity. To obtain accurate bearing capacity values, engineers conduct field tests that provide real-world data on soil behavior. Some common field tests include 1. Standard Penetration Test (SPT). The standard penetration test involves driving a sampler into the soil and measuring the number of blows required to penetrate a set depth. The results are used to estimate the soil's density and bearing capacity. 2. Plate Load Test. In this test, a steel plate is placed at the foundation level and loaded incrementally. The settlement under each load is measured, and the ultimate bearing capacity is calculated based on the settlement data. 3. Cone Penetrometer Test (CPT). The CPT involves pushing a cone-shaped probe into the soil and measuring the resistance to penetration. This test provides detailed data on soil strength and can help determine the bearing capacity at different depths. Bearing capacity and foundation design. The bearing capacity of soil directly influences the design of the foundation. Based on the soil's bearing capacity, engineers select an appropriate foundation type, such as 1. Shallow foundations. For soils with high bearing capacities near the surface, shallow foundations, e.g., spread footings or slabs, are often sufficient. These foundations spread the load over a wide area. 2. Deep foundations. For weaker soils, or when the soil near the surface cannot provide enough bearing capacity, deep foundations like piles or drilled shafts are used. These foundations transfer the load to deeper, stronger layers of soil or bedrock. Real-world applications of bearing capacity. 1. High-rise buildings. In high-rise buildings, the foundation must be designed to withstand the immense weight of the structure. Engineers calculate the bearing capacity to ensure that the soil can support the building without excessive settlement. 2. Bridges and roads. For infrastructure projects like bridges and highways, the soil beneath must be able to bear the loads from vehicles and heavy traffic. Bearing capacity calculations are crucial to ensure the stability of these structures over time. 3. Dams and retaining walls. For dams and retaining walls, which hold back large amounts of water or earth, the foundation must be capable of withstanding extreme pressures. Bearing capacity plays a significant role in preventing structural failure. Conclusion. The bearing capacity of soil is an essential concept for ensuring the safety and stability of foundations in construction projects. Engineers must consider several factors, including soil type, moisture content, and depth of foundation, when calculating the soil's bearing capacity. Using proper calculation methods and field tests, engineers can design foundations that will safely support structures for years to come. Thank you for watching Blueprint to Reality. If you enjoyed this video, please like, share, and subscribe for more expert insights into civil and structural engineering. See you in the next episode.